Hi everyone, I'm Borres from the School of Industrial Engineering and Engineering Management of Mapua University, and on behalf of Aaron Cornista, I'll be presenting a research study entitled Multivariate Analysis of Dissolved Air Flotation System at a Water Treatment Plant in Laguna de Bay. Clean water is one of the basic necessities of human beings. Although there's more than enough supply of water to support the increasing world population, access to sanitary water is limited. This is mostly caused by the pollutants released in bodies of water through the waste of human activities, specifically agricultural, domestic, and industrial waste. According to et al., the increase in urbanization results in the increase of waste discharges into water sources. This is especially true for countries surrounded by large bodies of water, such as the Philippines. Most of its region is within the medium to high risk in terms of water quality by the World Resources Institute of 2018. According to the latest census, the Philippines ranked number 13 in terms of total population with a growth rate of 1.72%. Among the country's 18 administrative regions, the most densely populated is the National Capital Region with a population density of 42,857 people per square kilometer. This is very high considering the national level where the population density is only 337 people per square kilometer. Because NCR is highly urbanized, its current water sources such as the Angat, Ipo, and Lamesa dams can only supply 6 million out of its 12 million inhabitants, based from the Metropolitan Waterworks sewerage system. This was a problem as well as an opportunity to look for obscure water sources. One such water is the Laguna de Bay. Laguna de Bay is located in the southwest part of Metro Manila. It is the largest freshwater lake in Southeast Asia with an approximate surface area of 90,000 kilometers squared, average depth of 2.8 meter and maximum depth of 6.5 meter. It has a high volume ratio which makes it turbid with spikes in ammonia and manganese during the major part of the year caused by the polluted inflows coming from various rivers. ASEAN countries continuously develop energy resources through the use of current demographics and frameworks to cope up with the rising demand in an affordable and sustainable energy source. The main pollutants in the lake are as follows: ammonia, manganese, total dissolved solids, and turbidity. This figure shows the cycle of ammonia in the intake. A rise in ammonia values causes significant taste and odor issues in the product water. It is an indicator of possible microbial, sewage, and animal feces contamination. Ammonia can be reduced by nitrification or denitrification procedures aided by ammonia microbes, usually on a packed bed or seared tank reactors. It can also be reduced through the use of UV chlorination. This figure shows the trend of dissolved manganese at the lake. High dissolved manganese in the product could react with the disinfectant resulting in the yellow color of product water. Though there are spikes and valleys from time to time, the manganese can be easily removed using oxidants such as potassium permanganate dosing. It would precipitate the manganese ion to manganese dioxide, which can be filtered out of the system. This figure shows a trend of the total dissolved solids at the lake. High total dissolved solids give the water an earthy taste and may contain minerals that may be harmful to health. There have been several spikes in the past due to the intrusion of Pasig River during high tides. Due to the size of particles, high total dissolved solids content can be removed using reverse osmosis membranes. Um, Lastly, this figure shows the trend of the turbidity at the lake. Turbidity refers to the light scattering properties of a sample. It is the haziness or cloudiness of the water. This is caused by fine particles scattering light at more or less 90 degrees to the direction from which the light enters the sample. These particles may incorporate sleets such as clay, small organic and inorganic matter, soluble colored organic compounds, algae, and other minuscule organisms. It's also used to indicate the health of the water source. high turbidity level can have adverse impacts on nature and society. There are many different pollutants that cause water to become turbid. These pollutants can be categorized into two, namely natural or background and human induced. Natural or background sources include erosion, riparian, stream bank, stream channel areas, and algae growth. On the other hand, human-induced sources include human activities such as mining, agricultural, and construction. According to Betts and Howard, the factors that affect water clarity or turbidity include suspended suspended sediments, algae water color, mixing certification, water levels, wind generated waves, sun position and cloud cover, and motorboat activity. Turbidity reduction is done using a sedimentation system or dissolved air flotation system. Dissolved air flotation is generally more effective than sedimentation, especially in algae-infested waters, such as the Laguna de Bay. This was also the case when sedimentation and dissolved air flotation system were compared in Tianjin, China, where microorganisms thrive. According to Edward J.K. 2009, dissolved air flotation, or DAF, is a process to clarify water by removing particles. This is commonly used in membrane plants or plants with granular media filtration. The process is summarized in the figure below. The raw water from the source is subjected to rapid mixing, where coagulant was closed. Coagulation process will start upon contact of the coagulant to the raw water. It will then pass through a tank where feculence is added to a slower mixing. Coagulated solids will form larger aggregates. The raw water and the solid will enter the reaction zone where saturated air is dosed in the system, making the aggregate solids float. It will then be separated with the water to scraping, and the sludge will be collected for treatment and disposal. A portion of the treated water will be recycled back to the saturation zone where air bubbles are formed through high pressure in the saturation tank. It makes air water system where will be used in the flotation of sludge in the reaction zone. Previous studies that determined the efficiency of DAF to treat high turbidity waters used pilot plants and experimental setup instead of full-scale plant. This has a significant difference as actual setup tends to have a significantly lower efficiency due to turbulence and higher flow rate. Also, each study and use different combination of factors in determining the significant factors affecting DAF cell. There's therefore a need to utilize a full-scale DAF system in this study, considering factors from operating parameters, water quantity, duration, and chemical dosing and nominal scale during high turbidity, and compared its factors during the turbidity season. The first objective of the study is to formulate an optimization model of the dissolved air flotation performance for different turbidity conditions. Second is to test the model on actual conditions to determine its effectiveness for different turbidity conditions. For the significance of the study, it can be used as benchmark for other wastewater and wastewater treatment plant that uses dissolved air flotation system. The study focused on the existing dissolved air flotation system of Potatan water treatment plant. The study was limited on the records and forms available from the plant, and the study was performed prior and during the Amihan season, where turbidity value shot up. In order to optimize a full-scale dissolved air flotation system, there were several items that were prepared prior to the experimental runs. First is the scope of flow and high turbidity was first defined, and second are the factors that have significant impact on dissolved air flotation on different turbidity levels were identified also. This was done by performing cluster analysis and multiple regressions on the historical data. Cluster analysis was used to group the historical data into different conditions of turbidity, high and low. It is a method of grouping objects that were very similar not only in one, but on several variables. Using historical data from June 2017 to November 2018, the variables included were only the inlet water quality parameters that had direct relationship inlet turbidity, TSS, color, organics. An agglomerative hierarchical algorithm was used using Minitab 18 statistical software, and the results were presented in the dendrogram below. Square Euclidean was used as the distance matrix, and the method was completed linkage. The jump of similarity level from steps 262 to 263 was the biggest among the steps, which is 10.071%, and therefore it was chosen as the number of clusters, which is two clusters. Cluster 1 contained samples with turbidity values ranging from 6 to 181 NTU. This was tagged as the low turbidity cluster, while Cluster 2 contained samples with turbidity values ranging from 182 to 400 NTU, were tagged as high turbidity cluster. Box plots of the four parameters used, turbidity, TSS, color, and organics, were shown in the graph. There were no literature showing the distinct differences between the low and high turbidity values. However, several literature suggested that around 200 NTU turbidities were already considered high. Therefore, the 181 NTU lower limited the high turbidity cluster was accepted. This definition of low and high turbidity was used for the rest of the experiment. Upon identification, the limits of turbidity level, multiple regression was performed for both clusters in order to determine the significant parameters. As mentioned in the previous chapter, previous studies showed that parameters used to optimize dissolved air flotation cells vary from study to study. Some use water quality and chemical closing, like what Alshani et al. Did using oil-water emulsion. Some focus on the operating parameters of dissolved air flotation, such as what Rubio et al. Mentioned. Others combined some water quality, chemical dosing, and operating parameters, such as Maysami and Caselan, Edwards et al., Palaniandi et al., and Bickerton stated, to be able to account the effect on various factors, inlet water quality factors, chemical closing factors, and dissolved air flotation operating parameter factors were included in a multiple regression. To account for the difference in human behavior during morning shift and night shift, a nominal factor, which was time per shift, was added in the regression. Aside from turbidity, there are 11 inlet water quality parameters included. First is the oxidation reduction potential. It's the potential that an oxidation and reduction reaction occurs. The level of oxidation reduction potential will define what form of chemicals exist in the raw water. Second is the total dissolved solid. It's a measure of the dissolved combined content of all substances present in the water that are smaller than 0.45 microns in molecular or ionic form. 3. Salinity. It's a measure on the amount of salts present in the raw water. 4th, conductivity. It's the ability of the raw water to conduct an electrical current with the dissolved ions as the conductors. 5th, in contrast with total dissolved solids, it's the measure of the solids present in the water that cannot pass through the 0.45 microns. 6. Ammonia. Usually in the form of ammonia nitrogen, it exists in water via natural liquefaction, domestic and industrial effluents, and sludge discharge. It produces taste and color issues in the water and reduces dissolved oxygen in aquatic system. 7. Manganese also exists in water via natural liquefaction, domestic and industrial effluents, and sludge discharge. It produces discoloration, metallic taste, and odor in the product water and clogging in pipes. 8. The level of dissolved oxygen in lakes and rivers is very important in the organism living in it. Low dissolved oxygen could lead to anaerobic condition where anaerobic bacteria could create substances causing color and foul odor in the water system. 9. pH is the measure of acidity and basicity of any water source. The level of pH is very important in the living organism. At pH lower than 5.8, certain algae species starts to deteriorate, and at lower values, other organisms will be wiped out. Temperature is the level of heat in the system. 10. The level of temperature has effect on the living organism as well. A certain level of temperature caters to the biodiversity in water sources. 11. Dissolved organic matter. Affect nutrient cycling, ecosystem productivity, UV light penetration, heavy metal transport, and drinking water quality of a lake system. The level of organic matter is approximated by UV254 measurements. There are 4 operating parameters included. First is recycle flow rate. It's the flow rate of the DAF treated water that goes to the saturator to be saturated with air. Second, saturator pressure is the pressure level to saturate the recycled flow rate with air to be used to float the coagulated particles. Saturator flow rate is the flow rate of saturated water that is injected in the DAF for the coagulated particles to float. 4. Influent flow rate is the flow of water entering the DAF system for treatment. There are two chemical dosing variables included. Oxidants such as potassium manganese. These are used to oxidize, transform manganese from a soluble state to a solid state which can be coagulated. Coagulants such as ACH are chemicals used to agglomerate particles in the DAF to form large flocks. Lastly, the shift time factors was included in the nominal parameter to account for the effect of personal attitude at different times of day. From table 4.2.1, the p-value for TSS is equal to 0.578. Color is equal to 0.965. Organics p-value is 0.098. Total dissolved solid p-value is equal to 0.447. Salinity p-value is 0.0363. Conductivity is p-value is 0.945. ORP p-value is 0.927. Ammonia is p-value 0.366. Dissolved manganese p-value equals p 0.388. Saturator pressure p-value is equals to 0.159. Saturator flow rate p-value is equals to 0.436, and time p-value is equals to 0.078 were all larger than 0.05. This means that their effects had no significant effect on percent turbidity reduction. These variables will therefore be removed in running the design of experiment. After removing these parameters, the second multiple regressions were executed. NOVA is as follows. From table 3, all the parameters were shown to have p-values lower than 0.05. Therefore, for the factorial experiment on low turbidity cluster, the 8 parameters were used: turbidity, influent flow rate, pH, temperature, dissolved oxygen, potassium manganese dosing, ACH dosing, and recycled flow rate. For the high turbidity cluster, below is the ANOVA from the initial run. From table 4, the p-value for the turbidity is equals to 0.218. TSS is equals to 0.988. Color is p-value is 0.756. Organic p-value is 0.992. pH p-value is 0.136. Temperature p-value is 0.244. Salinity is p-value 0.584. Conductivity p-value 0.61. ORP p-value 0.499. Ammonia p-value 0.598. Dissolved oxygen 0.354, potassium manganese 0.338, ACH 0.937, saturator pressure 0.439, and recycled flow rate is 0.863, saturator flow rate is 0.295, and time 0.367 were all larger than 0.05. This means that their effects had no significant effect on percent turbidity reduction. These variables will therefore be removed in running the design of experiment. Upon receiving these parameters, another round of regression was performed. The ANOVA is as follows. ANOVA table for the stepwise multiple regression of the turbidity cluster. From table 5, all of the parameters are shown that to have p-values lower than 0.05. Therefore, for the factorial experiment on high turbidity cluster, the 3 parameters were used: total dissolved solid, dissolved manganese, and influent flow rate. Upon establishing the factors that will be used for optimization for both clusters, the objective of this paper can now be achieved by performing factorial design experimentation on each cluster and by verifying the accuracy of the model. For the low turbidity cluster with 8 factors, a fractional factorial design is used with 1 replicate for each treatment. As one, there is only limited time for the runs, and second, there are some factors that are not controlled but we have to wait for them to happen, like inlet water quality parameters. The solution 4 was chosen, 1 out of 8 fraction with 32 runs. The values of the factors are shown based on the lowest and the highest recorded values of each of the factor in the low turbidity cluster. The experiment was performed from December 1, 2018 to January 3, 2019. The experiment was done in the actual DAF cell, and measurements were done in the lab for the water quality of check in the flow metal meter for the flow rates. The results were encoded in Minitab for multiple regression. For the high turbidity cluster with three factors, a full factorial design was used with one replicate for each treatment, as there is only limited time for the runs. There are some factors that are not controlled, but we have to wait for them to happen. Was chosen with 8 runs. The experiment was performed from December 1, 2018 to January 1, 2019. The experiments was done in the actual DAF cell, and measurements were done in the labor for the water quality and checking the flow meter for the flow rates. The results were then included in Minitab for multiple regression. From the mathematical model created for the dissolved air flotation system, the model was tested on actual conditions. The prediction and actual outcome were compared, and the experiment was performed from January to 14, 2019. The experiment was done in the actual dissolved air flotation system cell, and measurements were done in the laboratory for the water quality and check in the flow meter for the flow rates. It was apparent that 11 factors, including interactions, had significant effect in the percent turbidity reduction of the low turbidity cluster. Acetylcholine influent flow rate, total dissolved solids, dissolved oxygen, turbidity, pH, acetylcholine, pH, acetylcholine, pH, total dissolved solid recycle flow rate, turbidity influent flow rate, turbidity, pH, dissolved oxygen, and dissolved manganese, acetylcholine, dissolved oxygen, and turbidity. For a confidence level of 95%, 11 factors were significant. And here is the ANOVA table calculated from the experiment. The items highlighted in yellow were the factors that have p-value less than 0.05. This means that at 95% confidence level, they had no significant effect on the percent turbidity reduction at low turbidity cluster. It must be noted, however, that since the model was hierarchical, the values must be retained. The top four factors, turbidity 46.08%, acetylcholine influent flow rate 9.08%, acetylcholine dissolved oxygen 6.71%, and dissolved manganese 6.2%, constitute 68.09 contribution and the percent turbidity reduction. At low turbidity, percent turbidity reduction was more sensitive to changes in turbidity. Given the equation of turbidity reduction and that the final turbidity was the same, increasing the initial turbidity would increase the total percent in turbidity reduction. The relationship of acetylcholine and influent with regards to turbidity reduction was the effectiveness of coagulation through rapid mixing. Acetylcholine was injected to the influent and coagulation was induced through the high flow rate of the influent. A good combination of the flow and chemical doing would lead to improvement in turbidity reduction. This relationship of acetylcholine and dissolved oxygen with regards to turbidity reduction was the effectiveness of coagulation and aeration. High dissolved oxygen in the system would mean that the coagulated particles can be easily floated in the tank. The effect of dissolved manganese with regards to turbidity reduction was on the formation of manganese dioxide. High dissolved manganese results in color and added in the turbidity of the system. Based on the results on the coefficients of the table above, R squared is equals to 95.12%, which means that there are smaller differences between the observed data and the fitted values. The regression model for the low turbidity cluster is shown in this slide. In this figure, it shows the response optimization of all the factors in order to get the planned target, which is 80% turbidity reduction. The inlet turbidity should be 10 NTU, pH should be 8.2, total dissolved solid should be 400 ppm, dissolved manganese dosing should be 0, acetylcholine should be 1, influent flow is at 497.17 liters per second. Recycled flow rate is at 50.01 liters per second. And dissolved oxygen should be 8.88 ppm. This will give us percent turbidity reduction of 80%. Only total dissolved solid and influent flow rate are shown in the graph because the effect of the dissolved manganese is omitted as the effect is insignificant as well as its interaction to percent turbidity reduction. The items highlighted in yellow are the factors that have p-value less than 0.05. This means that at 95% confidence level, they have no significant effect on the percent turbidity reduction at the high turbidity cluster. As it can be seen, almost all except for the interaction of TDS and influent flow rate show a significant effect to percent turbidity reduction. It must be noted, however, that since the model is hierarchical, the TDS and the influent flow rate must be retained. On the other hand, we can remove the dissolved manganese factor as well as its interaction. Another run for ANOVA was performed without the dissolved manganese, and this is the result. The table shows that the TDS and influent flow rate has still a significant effect, but due to their interaction is still retained in the model. At high turbidity, only a handful parameters have effect on turbidity reduction as the capacity of dissolved air flotation is already reached. The saturators are clogged and the air could not push the solids upward, which caused the sludge to sink on the floor. The only parameter in the experiment that showed a significant effect is the joint interaction of TDS and influent flow rate. The combination of TDS and influent flow rate accounts the rate of dosing ionic salts in DAF. At high turbidity, the level of air to solids ratio is very much affected because during these conditions, the denominator is much higher than the numerator, and the presence of TDS has a significant effect on the solubility of air in the water. This results in a much lower air to solids ratio and lower percent turbidity reduction. Based on the results of the coefficients of the table above, at r squared is equals to 81.34%, which means that there are smaller differences between the observed data and the fitted values. And this is the regression model for the high turbidity cluster. This figure shows the response optimization of all the factors in order to get the highest turbidity reduction. The inlet TDS should be 350 ppm, dissolved manganese should be 0 ppm, and influent flow is at 500 liters per second. This will give us percent turbidity reduction of 69.49%. After the models are generated, this was tested in actual setting. The trial was done on January 3 to 14, 2019 at the plant. A plot of the predicted turbidity and actual turbidity is shown below for the low turbidity cluster and the high turbidity cluster. For the low turbidity cluster, the model was checked on 70 samples, and as you can see in the graph of the predicted values versus the actual values. The model shows high accuracy in predicting the actual values with percent difference ranging from 0.42% to 14.12%, with an average of 7.4% for 70 samples. Accuracy ranges from 85.88 to 99.58% with an average of 92.6%. A paired t-test was performed to determine if there was significant difference between the means, as it can be seen in the table. The p-value is equal to 0.423, which is greater than 0.05. Therefore, at 95% confidence, we accept the null hypothesis that the means are not significantly different, proving the validity of the model. For the high turbidity cluster, only 8 samples were tested as the amihan season was already finished and turbidity values entered the plant falls mostly on the low turbidity cluster. The model shows high accuracy in predicting the actual values with percent difference ranging from 7.78% to 16.77%, with an average of 11.88% for 8 samples. Accuracy ranges from 83.23% to 92.22%, with an average of 88.12%. As it can be seen in the table, the p-value, which is equal to 0.124, is greater than 0.05. Therefore, at 95% confidence, we accept the null hypothesis that the means is not significantly different, proving the validity of the model. The study confirms the difference in the efficiency of dissolved air flotation system at different turbidity levels using cluster analysis. Water quality data from June 2017 to November 2018 was separated into two groups: low turbidity cluster containing influent with turbidity values ranging from 0 to 181 NTU, and the high turbidity cluster containing influent with turbidity values ranging from 182 to 323 NTU. Result of the t-test showed that the following parameters have a significant difference, which is p-value less than 0.05 between clusters turbidity, TSSS, color, organics, temperature, and ammonia. For the low turbidity cluster, 5 main factors or 6 two-way interactions and 2 three-way interactions show significant effect in the percent turbidity reduction. The regression model generates as an R squared equals to 95.12%. The residual plots support the validity of the model. From the model, the ideal setting, which is percent turbidity reduction, is greater than 80%, was calculated, and the turbidity is equals to 10 NTU, and the pH 8.2, TDS is at 400 ppm. Dissolved manganese is 0. Acetylcholine is dosing is 1 ppm. Influent flow is 497.17 liter per second. Recycled flow rate is at 50.01 liter per second, and dissolved oxygen is 8.88 ppm. For the high turbidity cluster, only one two-way interaction shows significant effect in the percent turbidity reduction. The regression model generates as an R squared, which is equal to 81.34%. The residual plots support the validity of the model. So from the model, the ideal setting, which is percent turbidity reduction is greater than 80%, was calculated when TDS is equals to 350 ppm. Dissolved manganese is 0 ppm. Influent flow rate is at 500 liters per second. This was already the maximum setting. However, the maximum percent turbidity reduction that was reached was 69.4%. For the low turbidity cluster, 70 samples were gathered. Data showed that there was 92.6% accuracy on the predictions. A pair t-test proved that the means of the prediction and the actual were not significantly different. For the high turbidity cluster, only 8 samples were gathered due to the low turbidity entering the plant. Data showed that there was 88.12% accuracy on the predictions. A paired t-test proved that the means of the prediction and the actual were not significantly different. Thank you.